My screen is visible, slide is visible, and my voice is audible to you all.
Yes, sir.
Yes, sir. Audible, na? Okay, great. Sir. Okay, so now this will be the last session of the fourth day, in which I will be sharing with you two of my very significant case studies. And on both of the studies, we have published research papers, which I will share with you. And in this case, it is impact assessment study only. It is a kind of AI only, in which the direct use of remote sensing has been done. Means with minimal ground truthing, like 5 to 10% of the ground truthing, 90% of the work has been carried out using remote sensing. And land use land cover was the basic input in all this. So my case study one is geospatial assessment of tourism impact on land environment of Dehradun, Uttarakhand, India. Okay. Now you can see from the name geospatial assessment of tourism impact on land environment of Dehradun. Means if the tourism is increasing, if the tourists are increasing, it will have an impact on the land environment of Dehradun. Maybe due to construction of hotels, due to construction of parking lots, due to construction of temporary camps, or any one of this. Okay, there will be impact. So we will try to find out in this one. Now, the objective in this study was to assess the extent of urban sprawl over the course of time, how much urban area is increased, then to determine the land use unit of the study area and perform change detection studies. Means how much change has been done over a period of time, and to assess the impacts of tourism on Dehradun in terms of infrastructure development on various slope configuration existing in the area. Now, first I'll discuss a slide about the study area Dehradun. Here you can see the decision center Dehradun, and we have taken a study area 2 kilometers from Dehradun. We have shown all the places, rivers, mountains, everything in that. And you can see the circular study area. Okay, this is Dehradun. Of course, Dehradun is also called as Devbhumi because lot of temples are there. Then what methodology we have followed is this. First, we have collected the Landsat data. We have carried out land use land cover analysis of that. And parallelly, we have collected the digital elevation model, DEM also. And from that DEM, we have categorized slope. Okay. Using these four things, we have overlaid the land use land cover on the slope map, and we have tried to work out on what category of slope, how much built up has been superimposed. Okay. Now what you are seeing here on the screen is on left hand side, it is the false color composite image of Landsat MSS multispectral scanner of 14 November 1972. Okay, I hope now you very well know about FCC, and it is FCC image of 14 November 1972. And here this one can use land for analysis. You are seeing of the same FCC image with various classes like agriculture, forest, scrubland, water body, built up plantation and vegetation. Okay, so this is false color composite of 1972 and this is land use land for analysis of 1972. Then the left side what you are seeing is FCC image of 25th November 2000 and here you are seeing land use land cover image of 2000 only with the same FCC we have made on same classification. And the third one is of 2016. We did this study in 2016. So the latest one available with us is of 2016. Here you can see that this is FCC is clear. This built up area is increased as compared to the previous one where it was more patchy of vegetation, but here it is increased. Similarly, the land use land cover. Now, uh, as I told you earlier, we have to have the land use land cover inventory of classes which we are doing. So you can see that agriculture is reducing from 72 to 16. Built up is increasing. Okay, built up is increasing. Forest area also decrease, vegetation also decrease, water body also decrease, and other things are more or less remain same, but built up is increased for sure. Now it is imperative that wherever it is increased, some area of the same size would have been decreased, right? Because ultimately mass balance will be same. Okay, so I hope up to this point it is crystal clear to you up to land use land cover analysis because you have already seen that. Now this map On the left hand side is digital elevation model, popularly known as DEM. This you can download from USGS. What Anish has shown you on the first day, on the second day of the fundamentals of remote sensing class, satellite data analysis, and using the DEM, you can convert the DEM into various slope classes like gentle slope, strong slope, steep slope, moderate slope, extreme, and very steep. Like if it is 0 to 15 degree or 0 to 5 degree, it is gentle. Then 15 to 25.6, it is strong, like that. Okay. Like that, you can convert it to slow. This may look like difficult, but it is very easy. I will share one 5-minute tutorial with you. Just you need to give some command in QGIS, and it will convert the digital elevation model to slope map. Okay. Now our next task was to see how it is increasing. So here what you are seeing is that a build-up of 14 November 1972 superimposed over the slope classes. Okay, superimposed over the slope classes. This is built up of 25th November 2000 superimposed on slope classes, and same built up of 12th October 2016. And this is the combination of all. Here you can very well see that the color which is corresponding to 12th October 2016, it is even now coming onto the higher slope classes also. Here itself we can see that it is mountainous region. Still there we are seeing some patches of built up, right? Which was not there when we were doing this for 1972. It was almost clear, but people have started constructing house on higher steep slopes also, which is very dangerous. Okay, and then this is the inventory of built up on different slopes. So here you can see that most of the houses are increased on the gentle slope class. Okay, it is increased on the gentle slope class. Some are increased on moderate slope, and some are increased on strong slope also. And here you can see bars are there. Graphical bars are there. And even people have constructed house on very steep slope also, which is very dangerous. If there is a heavy rainfall, it may lead to landslide, and then it will be very fatal to the people living in the nearby area. Okay, so like that, up to this point, we have worked out the thing. And then we have tried to build a relationship between the population, tourist, and built up. So if you see, population, of course, it is increasing in Dehradun, 1970, and there was almost 1.9 lakh population. 1980 increased, and so on. And number of tourists also increasing. Okay, this data we have taken from Uttarakhand administration. Number of tourists also increasing, and built up also increasing. So there was a clear-cut correlation between the number of tourists and the built up, because what people will do is that since tourists are increasing and many people will be in search of cheaper hotels or cheaper lodge, they are constructing houses on their land by flattening the slope, and they are converting their houses to hotels and cheaper lodge. They are giving it to people, but ultimately what they are doing is that they are disturbing the land environment of that area. So this is how we can quantify. Okay, I told you in my first class that EIA is what? When we quantify the impact in terms of numbers. So see, everywhere we have not spoken any word subjectively. We have seen that, okay, if strong slope increase, how much is increased? Okay, moderate slope increase, how much increase? All these things we have increased. We have quantified. Okay, so then we were able to work out that it is solely because of the population and number of tourists influx. Because population increase is natural. Anywhere people are living there, their population will increase. But number of tourists are also increasing. That is leading to the more construction of hotels, lodge, and any other facilities. Okay, so what were our finding is that as Dehradun is a well-renowned tourist spot, number of tourists are increasing at an exponential rate, expected to be double by 2025, which is now nearby, compared to 1977, which shows tourist overburden. It is overburden. And from 1972 to 2016, built up is increased significantly. And of course, it may be attributed to increased tourist activity, and impact of tourism assessed by extracted and overlaid built up on slope maps, and it was observed in all slope categories. I've already shown you in all slope categories it was there. Okay. And the thing which is a matter of worry is that There was some part of built up observed on strong slopes also, strong, extreme, steep, and very steep slope also, which is more prone to landslide, as I said earlier. Therefore, it requires an immediate consent by regulatory authorities for forming strict bylaws. Okay, for infrastructure development for tourism activity and planning and management. So, like that, we have carried out this study. Now, I would like to hear from you. Any doubt in this one? Anything which you want me to convey to you so that we can discuss upon? I will keep the slide open anyway. Then we will move to my second case study.
Sir, overlay means weightage overlay or any other,
Yes.
sir? Like the overlay unless you are saying, no? Like
Mhm.
so it's like a weightage overlay. You have to set the parameters like which parameter is affecting the its right or
No,
something like
no,
that.
it is not parameter. I'll show you. See, first we work out the land use land cover analysis. Okay, 1972, 2000, and 2016. So built up classes are there. Now you can see here built up classes. Red one. Okay, red one. These built up classes we extracted and then we prepared the slope map using the digital elevation model. And all three
Okay, sir.
built up classes we overlay on the slope map, what you are seeing on the screen now. So parameter is built up area we have superimposed on the slope map.
Okay.
Yeah. And I already told you this slope map you can very easily make using a digital elevation model in QGIS. It is a simple formula. We always say it 1 in n, a slope of 1 in n, like this much horizontal I'll go and this much vertical I go. So basically 1 in 10 means 10 meter I'll go horizontal, then 1 meter I'll go deep. So whatever angle it is forming, it is called the slope. For this, ready-made tools are there in QGIS. It will ask DEM as input, and once you give DEM as input, it will create the slope map with various angles. And angles you can also give. If you want in different angles, that also it will give. But why I'm showing you this case study on fourth day is that because I wanted your knowledge base to be built in this last 4 days, which I believe that some delta X amount of advancement is there in your thinking from remote sensing and GIS perspective, so that you will be able to grasp more. You can ask if any further more. I would like. I'll be happy to take more couple of 1 or 2 questions. Then we'll move to my second case study. Then that will be the end of the training program in fourth day. Anyone? So shall we move ahead then? If no doubts in first case study. So okay, then we'll proceed with the second case study, which is one of my favorite, and that was the first paper by which I started my footprints in the research in remote sensing GIS. I will show you that. Okay. So now second case study is the impact of urbanization on microclimate of Nagpur city. Okay. I hope you all are able to hear me, and I hope you are able to see the slides also. So the second case study is related to impact of urbanization on microclimate of Nagpur city, a remote sensing approach. Okay, why I am specifically mentioning a remote sensing approach? Because because many times we know that climate change and global warming are major environmental issues in present scenario, right? And there is a continuous steady rise in worldwide temperature, that also we know, right? And it has been observed that urbanization, which is change in land use land cover, is it alters the land surface temperature. Okay, when you are constructing something by scraping the vegetation or the water body of that area, you will convert the city to a surface which has more temperature bearing capacity, means it will retain the temperature. And you must have observed that if you are moving onto the road or if you are moving onto the concrete road, you will feel more heat as compared to you are walking in a zoo where both side trees are there as well as some canopies there. Why? Because there the surface is not like that. At the same time, if I want to do some kind of modeling activity or some kind of decision making on that, measurement of temperature by sensor and thermometer will be tedious, time consuming and quite expensive. So in those cases, we try to use remote sensing. Okay. One thing. Second thing, recall my first lecture of second day. I told you that 80 to 90% of the time we will be working in the visible spectrum region, VIS region. But I have not showed you anything by now in thermal remote sensing. Okay, that is some other wavelength which I'll show in the subsequent slide. So in this particular research work, we use other band also. Okay, so our objective is to measure the land surface temperature using remote sensing. Now, I told you earlier that we okay. So I told you earlier that we'll be using between 0.4 micrometer to 0.7 meter visible region and up to near infrared also we can use. But in this case, we will be using thermal infrared band, which is from 8 micrometer to 14 micrometer. And I hope you are very crystal clear on these terms like reflection, emission and reflection. I very deeply I have explained you all these things. So uh, from EMR also we will be taking the readings for doing land use rent curve analysis, and whatever Earth is absorbed that it will be emitting, that also will use in our this present case study. So how we do is that I told you that day also that every satellite image, the smallest unit in that is called pixel. Okay, it is called pixel, and the numerical value on that pixel which represent that pixel is called a digital number. So first what we do is that we convert this digital number into spectral radiance with this formula. This is calibration formula. We use the digital number into spectral radiance, and then we convert that spectral radiance to land surface temperature. Okay, we convert that spectral radiance to land surface temperature. Now in this case also my study area was Nagpur city because I was situated in Nagpur. You can see here, and similar pattern you can see how we have done the places, roads, railways, etc. Now, first thing what we have done is that we have carried out on change detection analysis. Okay, change detection analysis. So this is the land use land cover map of 2005, which was categorized in classes like agriculture, open land, vegetation, water body built up. And this is 2008, 2010, 2016. Okay, so here you can observe very well that from 2005, some patches of agricultural land were there. Okay. But coming to 2016, this is almost nil and people have constructed houses on that, right? So if you see in last 11 years, from last means from 2016, because we were there in 2016, so we conducted up to 2016. From 2005 to 2016, the built-up was increased by almost 14%. That is from 55 to 69.84. Okay, 14%. And then agriculture decreased, Water body almost more or less and vegetation decrease and barren land is also decreased. So whatever increased is solely because of the built up. Okay, up to this point, I hope it is clear. And keep in mind, in this case also land use land cover is the base for everything. Then what we have done is that we have prepared some maps for emissivity. Now let me explain you emissivity. You already know. I already explained you in my first lecture of second day. What is emissivity? Emissivity is what? It is the ability to emit. Okay, ability to emit the absorbed radiation. So whatever EMR radiation the land has absorbed, okay, after some time it will emit in the atmosphere back. That emissivity, that emitted part will have longer wavelength, and that wavelength will be recorded by the sensor. So we have constructed emissivity maps using the emissivity formula. And you can see here the dark black is low emissivity, white is high emissivity. High emissivity means it will not retain the temperature with it and it will release the temperature. Okay, it will release the temperature. So this is emissivity of 2005. This is 2008. This is 2010 and this is 2016. So here you can see that it is slowly become, the Nagpur city has slowly become a city which has low emissivity. It has become more black. See, all blackish areas. Okay, all blackish area. Earlier, at least it was some white patches and some gray patches were there. But up to 2016, it is almost blacky area. Right. So it has converted to an area where emissivity will be low and temperature will be high. Now, based on these three things, base map, land use, land cover, and emissivity, we created land surface temperature maps. And you very well know the formula I have showed in my second slide. So this is the land surface temperature of 2005. Here each value represents a temperature and highest temperature was observed of 45 to 46.2 degrees Celsius. This is land surface temperature of 2008. This is land surface temperature of 2010. This is 2016. Here again you see it is converted to become more on the more reddish side. Means it is retaining the temperature with it. Okay, it is retaining the temperature with it. You can see here. So because they constructed houses, they did urbanization, and they have converted the Nagpur city into a low emissivity region, temperature is more. And then we have worked out the areas. So here you can see these all areas are there where temperature is low, like A Shukravari Lake, Ambazari Lake, Futara Lake. Of course, on the lakes, temperature will be less. Then VNIT Nagpur, Visvesvaraya National Technology, Seminary Hills, and CSR near Nagpur, where I used to work. Their temperature was low because all these are areas with higher greenery and water bodies. But there are certain areas like airport. You can see at this airport strip is also seen in there. Airport, Kachimet, Dava, Narayan, solid waste incineration in Padi. Here you can see this K is a solid waste incineration plant. So you know the microorganisms in that solid waste site, they will do some exothermic reaction. And that exothermic reaction is also captured in the radiance of the satellite sensor. So this is how it is done. We could work out land surface temperature. Now, if you see the statistics, there was a clear-cut correlation that mean land surface temperature is increasing. And in last 11 years, it was increased by 4.6 degrees Celsius, which is a good number, a good and alarming number. Okay. And if you try to see the workout, the correlation between that with increase in agricultural land, temperature was decreasing. With increase in open land, again temperature was decreasing. With increase in vegetation, again temperature was decreasing. Only when the built-up is increasing, temperature is also increasing. That means it is solely because of the increase in built-up over the years. The urbanization, what I was saying. Okay. And we try to see if we replace the 30-meter of the road, 30-meter of the area nearby the roads with tree, what will happen? So suppose there are no trees and only road and it is a barren land, the average temperature will be 44.7 degrees Celsius. Okay, but if I replace it with trees, the average temperature will reduce by at least 9 degree and it will be 35.4. So there will be a reduction in average temperature of around 9.3 degrees Celsius in the road buffer system, that is nearby road, if it is loaded with trees. And over the whole city, it will be decreased by 0.2 degrees Celsius. Okay, 0.2 degree Celsius. So you can understand the importance of greenery in an urban system. And this green infrastructure has a lot of benefits with it. Like we will have access to green space, plus it will reduce the urban heat island effect. It will improve the air quality, and it will increase the landscape connectivity, right? Noise pollution also will be less. Carbon sequestration will also be there, and it is also useful in managing stormwater. Okay. And you see, if remote sensing was not there, I would not have done it, because I already showed you this time also I'm showing you that it provides data for large areas, provide data of very remote and inaccessible areas where I cannot go. And also it is possible to monitor any anthropogenic or natural changes in the landscape because of the remote sensing satellite. And of course, it is relatively inexpensive when compared to employing a team of surveyors, right? Easy and rapid collection of data and rapid production of maps for interpretation. Okay. With this, the second case study also gets over. And I would like to take a couple of questions or some query or some viewpoint. If you would like to share, I'll welcome you all. Anyone? Anyone would like to share anything? Or if you have any question, you can ask me.
Sir, the MSCVT part,
Hmm.
I didn't get it.
Okay. I'll share again. Emissivity partner.
Yes, sir.
Okay. So emissivity. Okay. So first thing is that can you recall my first lecture on second day in which I said about absorption, reflection, transmission, and whatever absorbed it will be emitted back. That much can you recall?
Yes, sir.
Okay. Now, you see what kind of entities will be able to absorb the things and emit it back. Okay. I'm giving you options like trees, water bodies, built up roads, or any hard material. Out of this, which material will be able to retain more? Any EMR spectrum, and later it will be able to emit.
Yes, I didn't get what you're saying.
No, I'm asking you up to emissivity, you are clear, right? From day
Yes,
two,
sir.
day two lecture.
Yes,
So
sir.
I'm asking you if I'm giving you 5 land use classes like trees, water bodies, built up roads, and other hard structure, anthropogenic structure. Out of these 5 land use classes, which classes will more retain the temperature?
Build-ups,
Hmm?
build-ups,
Hmm? Then apart
and
from built
roads.
up roads, yes. Okay, okay, you understood actually. Okay, so you built up and rows will uh, retain the heat. So you see here, if you see the land use land cover map, you see central part is vegetation, right? You can see here more. So in the emissivity case also, central part emissivity is high, means it will not retain, right? It will not retain. It will release the temperature. But if you see the built up part, as you said, green color, the emissivity part is low, which is what you said that it will retain the temperature because it has low emissivity. So emissivity we have prepared based on the land use classes. Now question comes with which formula? Okay, so there are two formulas for it. One is split window algorithm. One is moving window algorithm. That when I share my paper with you, that you will come to know. So what you have to do is that you have to give input of this land use land cover map, this map, and you have to apply that formula just like you will be applying this formula. Digital number to spectral radiance to land surface temperature. This can be applied in QGIS also. Okay, like that only you have to apply the formula. Only thing is that in that case, this input will be your land use land cover, whatever you are doing. Okay, you will give the land use land cover input, you will apply the emissivity formula, and you will have the emissivity maps like this one, what I have shown you. But concept, I hope it is clear to you. The lower the emissivity, the more temperature it will retain.
Yes, sir.
Anyone else?
Sir, by using this emissivity, we can able to emissivity, we can able to track the greenhouse gas emissions from the agriculture field.
Greenhouse gas emissions.
Yes, sir. By using this emissivity, we can able to track the greenhouse gas emission.
Yes, there are satellites for that. But the problem in those satellites is that by now we don't have any satellite for high resolution. Means they will be giving a value for, let's say, 200 kilometer by 200 kilometer, only one value. Like this much is the methane, this much is the carbon dioxide, and other parameter. So methane very well, greenhouse gases can very well be worked out using satellites, but by now we are not able to work it out on high resolution. We have very low resolution satellites. Anyone? Any more questions? I hope both the case studies are clear to you. Except emissivity, any new concept was not introduced, except emissivity and slope map. But both can be done very easily if you have done properly the hands-on QGIS with Anish. Same principles will be used. So if no further question, thank you all for attending this course up to the fourth day, and I'll share the recording immediately. I'll try to share the recording immediately, and I will also